As you guys have already heard, I'm Dave Graff. We met the last couple of days in the PPMS room. We're going to talk about measuring Fermi surfaces in extreme magnetic fields. If we have any time at the end of talking about the extreme magnetic fields, we're going to talk about high pressure measurements. But we'll see if we have time to actually get there. We're going to talk about different techniques that we use to measure the Fermi surface. And also, I've tried to use a lot of examples of data we collected here at the Magnet Laboratory when we're discussing how to measure these Fermi surfaces. OK, so jumping off point, our starting point, the electron energies have to follow Schrodinger's equation to follow what energies that the carriers have. So just the kinetic energy is proportional to k squared, right? So we end up having this quadratic equation here versus energy. And knowing this gets us pretty far with materials, but it doesn't tell us why a material behaves as a metal. Okay? So then we start to incorporate boundary conditions. If we have a lattice spacing of A in reciprocal lattice space, the boundaries will be at plus minus pi over A. And by determining the standing wave solution with these boundary conditions in place, a gap begins to open up at the edges of the boundaries. In the extended zone scheme, we get these energy bands that go off into infinity. But if we fold them back onto the same plot, we have the reduced zone scheme here. Okay, so we have bands of energy that describe where the electron energies could be. But where the energies actually move and interact is at the Fermi level. So if we have the Fermi level going through an energy band in the middle, it's a partially filled band. And that means that the electrons can move around. They have the possibility of shifting energy. If the Fermi level goes between energy bands, then we have a completely filled band and a completely empty band. And there's not the possibility of electrons moving around. So this describes why a material is either an insulator or a metal. Partially filled bands give us metals. That doesn't really tell us, though, what a Fermi surface is. The scientific sounding explanation of what a Fermi surface is, probably taken from a textbook, is the location and reciprocal space of long-lived electronic excitations that govern the electronic properties of metals at low temperatures. That's kind of a mouthful. It doesn't really tell us what it is, though. It's kind of the fundamental property we chase down for materials in the metallic state. Okay, this gives us an idea of some of the shapes we have of Fermi surfaces. If you have a 1D Fermi surface, you have flat sheets, okay? And if they bend a little bit, we call them quasi one-dimensional. And if they wrap all the way around and they can form a cylinder, this would be a two-dimensional Fermi surface. And if they get pinched off at the ends or they have some warping or corrugation along the side, you have a quasi two-dimensional Fermi surface, and they can be completely closed off. It doesn't have to be a sphere. It could be shaped like an egg or something like that. You can have a 3D Fermi surface. What I think about it as is it's the pathways for carriers through a metal. Okay, holes or electrons travel along these highways through a material. That's the space they can actually move. Okay, so we're going to talk about measuring Fermi surfaces, but one thing we can do is actually start off with a guess of what the Fermi surface might look like. So before we even do a measurement, we can just grow crystals and get some information and make this initial guess what we might have. And this work was done here at the MagLab by Luis Belicas's group. They made single crystals of this material. They put it into an X-ray diffractometer, and they got out the lattice spacing of the material. They also took a guess at where the Fermi level would sit in the energy bands, and they put all this information into prepackaged software called Wien2K. I don't know if any of you have heard of it before, but this is pretty popular. You can buy this kind of like you'd buy Microsoft Office or something like that. It's already been, the programming's been written out for you, and you put parameters into it, and it'll give you back band structure calculations and an estimate of the Fermi surface. And it told them for this material that it's going to have some wavy quasi one-dimensional Fermi surface sheets, the yellow and blue shown here, and some closed 2D Fermi surface as well. So usually when you do measurements, you can refer back to calculations and see how close that they are, how good of a guess that you made initially. Okay, but let's look at some real examples working our way back in dimensionality. Let's start with 3D Fermi surface. Okay, a simple example is sodium. It's group 1 of the periodic table. It's body-centered cubic lattice for a single crystal of sodium. And it's got one 3s valence electron. Okay, so if we look at the energy band structure of the material, the Fermi level doesn't cross it at very many points, and that ends up giving us a pretty simple Fermi surface. The Fermi surface basically looks like a sphere, almost a sphere. And that's true of all of the elements of group 1 of the periodic table. They'll all have this S-shell electron, and they'll all have a similar Fermi surface shape because of this. But if we go to a more complicated 3D example, we could, for example, think about cobalt. It's in group 9 of the periodic table. It's a hexagonal close-packed structure, but it has, because it's in group 9, it has a number of valence electrons and many band crossings at the Fermi level. And because of that, the Fermi surface is much more complicated. Okay, so if you put cobalt, a single crystal of cobalt, into a high magnetic field, you'd end up with a number of Fermi surfaces and complex data to analyze data later. So to move back from 3-dimensional examples, let's think about a 2-dimensional example. Some common materials we measure here are cuprates. Okay, we have these copper-oxygen planes separated by other stuff, but because the electrons are moving in these planes, we call it 2-dimensional material. So if we looked in just one direction at the dispersion relation, we'd end up having that quadratic dispersion relation again. And with a partially filled band, we'd have the Fermi level partly filling it. If we had the same thing in the x and y direction, then we can have a circular sort of energy relationship, and this would be the path of the materials. If it's isotropic vertically from here along the z-axis, we'd end up having a perfect cylinder. Okay, circular shape, make it grow vertically, a perfect cylinder, but most of the time nature gives us kind of a warped or stranger shape. Okay, so this is our 2-dimensional cylinder, a 2-dimensional Fermi surface, and this is the pathway of the carriers around the edge of it. We don't have to have just one Fermi surface in a 2-dimensional material. You can have a number of them. So for an example from James Analytis' work, we have strontium iron phosphide, and this is predicted to have 4 different Fermi surfaces, which is what they saw with the measurements. 4 different quasi-2-dimensional Fermi surface shapes. Okay, we can back up to one more dimension and think about 1-dimensional Fermi surfaces. Okay, and this is a molecular conductor, stuff that I did way back in graduate school. So this is based on complex molecules, but it actually gives us kind of simple physics to think about. If you take this TMTSF molecule, it looks like this. And if you stack them vertically in this figure, the pi orbitals of the molecules overlap, so the carriers want to move in this direction, in chains. Okay, and the rest of the material, the PF6, just sits out here and kind of creates a buffer between the chains. It just kind of separates the chains. So for the most part, carriers just move in 1-dimensional motion. Now for a perfect 1D system, we have these parallel Fermi surface sheets. Okay, the real space velocity of any energy surface is the gradient of the energy surface. Okay, so if we have Fermi surface sheets extending in the z and y direction, that means in real space that the carriers are moving in the x direction. And that's what happens here with this quasi-1D material. It's actually moving along the x direction easily, but it can also kind of hop around in the other 2 dimensions. So instead of having perfect 1D sheets, we have these quasi-1-dimensional Fermi surface sheets. What's interesting about these sheets is that if you look down for a top view on this figure here, you'll end up seeing these kind of 2 warped sheets next to each other. And these quasi-1-dimensional Fermi surfaces have the interesting property that they can nest onto each other. This Q vector describes the way that if you shifted this Fermi surface over, it would map onto the one next to it. What that means, all the carriers on these Fermi surfaces can be involved in kind of drastic changes to the material in phase transitions. So let me show an example. These equations at the top just kind of basically talk about how an electron gas responds to the dimensionality of the material. And what it really shows is for the 1D case versus 2D or 3D, there's an instability when the Fermi surfaces are 2 kF apart. Okay, so in our one-dimensional Fermi surface case, because they're 2 kF apart, we have an instability against phase transitions. And very interesting things happen when we have this case. We have a metallic state at room temperature. So we have equally spaced lattice points and a uniform electron density and a partially filled band. It's a metal. Okay? Now when we cool it down, we get some energy gain from shifting points of the lattice closer together. They start to form these pairs or dimers. And it costs energy to move the lattice around, but there's a gain in energy because the overall electronic energy is lowered because a gap begins to form because this lattice is shifting. Because there's new positions in the lattice, the electron density changes and forms around these new lattice sites. So there's a charge density that has a periodicity, so it's a charge density wave. And when something forms a charge density wave, because a gap opens up at the Fermi level, it becomes an insulator. So this isn't just some theoretical idea. We, of course, can measure this in real samples. And this example is another organic material. The parylene molecules are just made by 20 carbon atoms together. And this cartoon off on the side kind of shows how things stack. The parylene is represented by these blue blocks here. And they go up vertically in chains through the figure. And again, this anion just presents stuff to make fillers around these chains. Okay, again, we have these one-dimensional chains. So what happens when you cool it down? We have a log-log scale here of temperature versus resistance. It starts off at room temperature as metallic. And as you cool down, when you reach about 20 Kelvin, the lattice begins to shift. An energy gap begins to open up. And the resistance begins to increase, almost a couple orders of magnitude as you cool down the rest of the way. Okay, so what can you do with something like this in a strong magnetic field? What's the point of this? Well, if you put this in a strong magnetic field, then you continue to do these temperature curves. Energy bands have carriers of up and down spin. And Zeeman splitting will split these energy bands, and it'll close the spacing between the energy gap. And the carriers can more easily overcome this gap. So the transition temperature shifts to lower and lower temperatures. So then we kind of make this phase diagram of the transition temperature where this density wave transition happens as a function of magnetic field. And as we shift out in magnetic field, the transition temperature moves to lower temperatures. So to the maximum field in one of our magnets, 35 Tesla, we can lower the transition temperature by up to 60%. This isn't so much a measurement of the Fermi surface as a way we can manipulate the Fermi surface for these quasi one-dimensional materials with a really strong magnetic field. Okay, to get into talking about the electron motion, we have to at least look through the math of where the description for these Fermi surfaces comes from. Okay, I didn't develop this math. I found it in Griffiths. No surprise there. Okay, but we can't just talk about the carrier momentum because we're working in a magnetic field. We have to include the vector potential. And the curl of the vector potential is the magnetic field, in case you've forgotten. In this case, we're choosing the vector to be along the y-axis, and the field is along the z-axis. So if we include the vector potential in the Hamiltonian, and we go through all the math, the energy levels we get follow these solutions to a harmonic oscillator. The important takeaway message is that we get discrete energy levels like the harmonic oscillator does when we include a magnetic field. Okay, so Cattell's book has this nice figure in it that kind of explains well what's happening. At zero magnetic field, we have this Fermi sea of electrons, okay, just kind of this continuum of energy. But as soon as you turn on a magnetic field, these energy levels coalesce. We have these discrete energy states, and the space between them is proportional to the strength of the magnetic field. Okay, when you increase the magnetic field further, these energy levels start to shift up and then past the Fermi level. Okay, so as you're increasing the magnetic field, when these energy states pass the Fermi level, you get a quantum oscillation. And when the level gets past the Fermi level, the carriers fall back down into the next energy state. So as you're sweeping the magnetic field, you see oscillations in sample resistance, magnetization, et cetera. Okay, these discrete energy states are very clean and sharp if you have a clean sample that's been grown or at very low temperatures. That's why we can't measure Fermi surfaces at 300 Kelvin or room temperature. Okay, so for our measurements, we have to have clean samples and low temperatures. So as soon as you turn on a field, you have discrete energy levels that we sometimes call Landau levels. Okay, so what does this really mean for a Fermi surface? Here's our picture from the previous slide. We have our discrete energy states. So what if we have a spherical Fermi surface? That's this dashed line around the outside here. We turn on a magnetic field, and these Landau tubes form. Okay, if the field is perpendicular up, top, bottom through the slide. Okay, and if the field increases, these Landau tubes move outward and past the spherical Fermi surface, and we'll see quantum oscillations. So the question is, why do we have these discrete orbits for the electron, where they move around the outside? And this comes from the Bohr-Sommerfeld quantization rule. Again, lots of math, the equation of motion for the electrons and its momentum. But the important part is that the amount of flux that goes through the real space area of these orbits is quantized. The minimum amount of flux that could go through these orbits is a quantum of flux. Okay, we can use this relationship to find out the next important thing that we really want to know, which is how far apart are these tubes in their spacing. Okay, when we see this data, what's going to be the periodicity of the quantum oscillations? Okay, so we have a relationship between the real space area of these orbits and the k-space area. And when we go through this math, we find out that the spacing is periodic in inverse magnetic field. Okay, so when you sweep a magnetic field, you're not going to see quantum oscillations that are evenly spaced in magnetic field. They'll be evenly spaced in inverse magnetic field. And we also come up with Onsager's relation. What this says is that the frequency of these quantum oscillations is proportional to the area in k-space that the orbits take up. Okay, so now that we have our rules, we can actually think about some data. So we turn back to an organic conductor with this very long, complicated name here. These are the donor molecules, and that means they donate electrons. But really, once again, we can represent them as bricks. Okay, so we have this stack of bricks here, and if you looked at an end-on view of this lattice structure, you'd see kind of this grid pattern. And the pi orbitals from these molecules overlap. All that really means is that where the molecules overlap, you end up having these conducting planes with the blue shading here. Okay, in this type of two-dimensional structure, of course, it's not just for organics. You can have this in rutheniates, cuprates, pnictides, any number of materials. Okay, it has these two-dimensional conducting planes. So what happens when we take the magnetic field and we apply it perpendicular to these conducting planes? Okay, here's our blue Fermi surface. It's cylindrical. And we've turned on a magnetic field, so these red cylinders represent the Landau tubes, these discrete energy levels that form beneath the Fermi surface. And when we sweep the magnetic field, these Landau tubes, these energy levels are going to move outward past the Fermi surface. And for some actual data, we see for resistance, it's called the Shubnikov-de Haas effect. Okay, the resistance of the sample shifts up and down as we see the quantum oscillations. We can also see some of the things that we already talked about, that as we get to the lowest temperature, half a Kelvin, certainly the data is the most obvious. And as the temperature increases, the oscillations fade away and we can barely see them. And also that the spacing increases between the oscillations as we move out in magnetic field, because it's not uniform in magnetic field strength. The spacing is uniform in inverse magnetic field. So if we take our lowest temperature data and we plot it versus inverse magnetic field, you can see the spacing is periodic. It's evenly spaced this way. And in inverse magnetic fields, you can take a fast Fourier transform of the data, and we find that this has a frequency of 494 Tesla. We can use Onsager's relation to say, okay, we have this frequency, that's some area in k-space, and once you know the area in k-space, you can compare it to what fraction of the Brion zone does it take up, for example. You can also compare it to band structure calculations. Yeah, go ahead.
How do you do the background subtraction?
That's a good question. For the most part, it's really a more hard question recently, because if somebody has low frequency data, which is a big problem with all these direct fermion systems that they have low frequency oscillations. Majandel's nodding because he's had this exact problem. Normally we subtract a polynomial, but if you use a higher order polynomial and you subtract that away from your data, then it can create oscillations, right? If you use like a 9th order polynomial, you have your data and the polynomial waves around it and kind of creates these false oscillations. So really the rule of thumb is don't get higher than a 3rd order polynomial. And if you just want to check out the spacing of the oscillations, you can make a derivative of the data, and that'll just show the change in slope and kind of ignore the background. But yeah, removing some backgrounds can be challenging. OK, what if we take the sample and we rotate it in a magnetic field? Here's Onsager's relation again that relates the frequency of the oscillations to the k-space area. Here's our Fermi surface with the carriers moving around in a circle here. The field is perpendicular. And this yellow space indicates the k-space area for the orbit. If we rotate this cylinder, this Fermi surface, you can see this k-space area is getting larger. So the frequency we're going to measure is going to be bigger. So we usually plot our frequency versus the angle, and we get a relationship like this. When it's 0 and the field is directly along the cylinder, we'll get the lowest frequency. But as this area gets larger, the frequencies get larger as we move out an angle from that point. If it's a perfect 2-dimensional cylinder, it'll follow the smallest frequency over cosine theta. But of course, not every Fermi surface is a perfect 2-dimensional cylinder. Most of the times, they're not. For some real data for barium iron arsenide, for example, we see the frequency dependence for the angle like this. You can see as you rotate this sample away from 0, this frequency barely changes at all. And that means that it's a closed 3-dimensional Fermi surface shape, almost a sphere, something similar to that. But the green and the red data show this extrapolates out to perhaps being a 3-dimensional Fermi surface. And this one follows almost some kind of 1 over cosine theta behavior, so it's closer to being a quasi 2-dimensional Fermi surface. OK, so rotating the sample tells us a lot about the shape of the Fermi surface. OK, so there are issues with using a fast Fourier transform to look at your data. Now, this is data, once again, taken by Luis Belikas here at the MagLab. It goes up to 45 Tesla in the hybrid magnet. So he's got a couple problems here. Not that many problems because it was published in PRL. But as you sweep the data, you can see some oscillations start to form. And if we take the data and we subtract the background away, we'll see these oscillations versus inverse magnetic field. We can see there's distinct equal spacing between them. So you can use a fast Fourier transform. But when you have small frequencies or very few oscillations, then the peaks from the fast Fourier transform kind of bleed together. It's kind of hard to separate them out, compare their amplitudes. Again, for this study, they were able to complete it. But one approach to this would be to just try to improve your technique. Maybe you can see the oscillations down to lower fields. The more oscillations you see, the easier it is to analyze. But you can't always do that. Sometimes unique problems come up. For example, with Suchitra Subhaschan's work, she was doing a quantum oscillation study of cuprates. Well, there sometimes they superconduct out to 20 or 30 Tesla. So most of the measurable magnetic field has been taken away. So this might be the usable amount of magnetic field where it's actually in the normal state, and you can see quantum oscillations. What can you do about something like this? Well, like I said, in Luis's case, maybe he could clean up his data. It was certainly good enough to be published. Or you can try to pursue more quantum oscillations. In Suchitra's case, she took the same type of material out to Los Alamos. And you can see this is the stopping point for the hybrid magnet. And she picked up 55 Tesla of additional information by pulsing this, using this in a pulsed magnet to 100 Tesla. Okay, having the additional magnetic field certainly gave her more quantum oscillations. And when she FFTs the data, there's 3 distinct peaks that show that there should be 3 different orbits to the material. I think you'll see a film at some point during the week about the pulsed field facility in Los Alamos. We can't do all the same measurements we do here in Los Alamos. There are some drawbacks to being able to get to 100 Tesla. You have to do your whole experiment in tens of milliseconds, so that can be difficult. you're pulsing kiloamps of current through the magnet over that short time scale, which is kind of a violent burst of energy, so the magnets can vibrate. But in some cases, it works out that you have this additional amount of magnetic field. This was a clean result, and it certainly gave her more quantum oscillations, which gave her a cleaner description of what's going on with the Fermi surface. Okay, so we've seen some different data, but how do we actually obtain that data? How do we measure the Fermi surface by different techniques? One of them Eric was talking about a little bit, AC susceptibility. This is somewhat similar to the VSM in that you take a balanced coil set. So that's inside with this white background, this balanced coil, and they're pretty small. I'll talk about them more in the next slide. And on the outside of them, we put an excitation coil. And when you put on some small AC field, maybe on the order of a millitesla, you can detect changes in the sample through one end of the balanced coil set. So this measures changes in magnetization, which we call the de Haasmann-Elfin effect. This is the dilatometer that Eric was talking about, and I'm glad we have a schematic of it up here because it's a brilliant design. It looks really complicated, but it's actually a very simple idea. This is the reference to George Schmiedishoff's paper, how he designed and constructed it. But if you look at this apparatus, it's just a parallel plate capacitor. This plate up here is fixed at both sides, and this lower plate to the parallel plate capacitor is resting on a foil spring, so this can move up and down. And this lower plate has a point that's touching the top of a sample, and that sample's fixed in place. So if you sweep a magnetic field and you see quantum oscillations through a dimension change in the sample, say it's getting longer and shorter as the field sweeps, then you'll see a small capacitance change there. And as Eric said, we can measure capacitance very, very accurately. This isn't our first approach to measuring quantum oscillations, but it is possible. Rick had in his talk yesterday that to test the quantum design dilatometer, they put elemental aluminum in their dilatometer, and they saw very large quantum oscillations. A lot of times this is used to chase around phase transitions, but as Eric mentioned, you can see nanometer or smaller changes in the dimensions of the sample. Pretty amazing resolution. Another way to measure Fermi surfaces is again through torque magnetometry. I saw Eric discussing this a little bit as well. Here's a block of a sample on this foil cantilever, usually made out of beryllium copper. And there's also a bit of copper foil beneath this bit of foil, and they're separated by some insulator, a little bit of G10, something like that. And we measure, again, as a parallel plate capacitor, the capacitance between these two pieces of metal. When we sweep the magnetic field and the magnetization of the sample changes because of quantum oscillations, this foil wants to move up and down, and we just measure the capacitance of it. This works in a lot of cases and for larger samples, and we can use different thicknesses of foils. And that lets us this be very versatile, but it's not the most sensitive option. So we also have these piezo-resistive cantilevers. I saw Eric talk about them a little bit, but it's better to hear something twice than not at all. So these were actually developed as AFM tips. So when you buy it from the company, it actually says on the box it's an AFM tip. But the way they were measuring the surface of a material with AFM was because of these changes in resistance. And the actual changes in resistance just come from these points where the lever arms are attached to the body. Okay, so there's a resistance path that goes up here and a matching one that goes here. So if this lever arm moves, then the resistance will change. So we just take these two resistors here and we incorporate them as part of a Wheatstone bridge circuit. The two more resistors at room temperature. We have a couple potentiometers outside our breakout box, for example. And when these four resistors are put into this configuration, we cool down our sample to low temperatures. We start at zero field, and we balance the circuit out so it's at zero for our lock-in measurement. And when we sweep the magnetic field, as this sample tries to move up and down as its magnetization changes and creates torque, then we'll see the voltage signal oscillate about zero. Okay, like Eric said, this is incredibly sensitive, but these don't bend, they just snap off. Okay, so oftentimes you're sweeping the magnetic field and the data just goes away because they're sensitive but delicate. Of these four techniques, the two at the top can be used to measure any shape of Fermi surface. Even nearly isotropic Fermi surfaces, But to create torque, you have to have a change in the shape of the Fermi surface. Okay, this term means that the frequency is changing with angle. So if you have a spherical Fermi surface and you try to measure it through torque magnetometry, you won't create any torque. You won't be able to measure it. The same is true of a perfect 2D cylinder. If you take a sample like that and attach it to a torque magnetometer, at theta equals 0, it won't create any torque. So a lot of the times when people are doing these kinds of measurements, they'll tilt the sample a little bit away from theta equals 0, where the Fermi surface is changing shape a little bit to create some torque and make the measurement easier. Okay, a little bit more about AC coils. This is kind of a nuts and bolts explanation of how you would actually build one of these things. So if your advisor or supervisor gives you the task of making this, how much of your life you're going to waste working with really fine wire. So this rectangle out here represents the drive coil. Okay, this can fit inside a pressure cell sometimes, so the entire width of this assembly might be as little as 3 or 4 millimeters. Okay, and inside the excitation coil, these orange spots, these blue spots are the detection coils. Okay, these are wound on what we call a former. So it's usually some piece of plastic, G10, something that's magnetically inert that you can't see magnetically. And you'll find wire on these on both sides. It's usually thousands of turns of wire, and the diameter of the wire might be between 12 and 50 microns. Okay? When you get thousands of turns of wire on there, usually as you're doing it, you're wet winding it. You're putting epoxy between the turns to fill up space because you don't want the turns to vibrate. That creates noise. When you wind all the windings on there, you take your former with the coils in place, and you stick them into the excitation coil, and you make some small AC field with the drive coil, the excitation coil. And when that happens, you see how much of a signal you get in the detection coils. You pull it back out, and you adjust the amount of windings around either end on the former until when you finally test it, you see almost 0 signal. Okay, so that's a balanced coil set. And when you have a balanced coil set of detection coils inside the excitation coil, and you put a sample in just one end of the detection coils, like shown here and here, you can detect the magnetization of the sample. So yeah, it's not that easy to put these together, but they're incredibly sensitive. So I did this measurement here in the PPMS that you guys have all visited. There was 77 hertz frequency of a 5 milliamp drive into the excitation coil. The red line here shows the data that was collected on a lock-in. As I sweep the magnetic field from 4 to 16 Tesla, you can see that it changes maybe 70 or 80 microvolts in the signal. It doesn't look very exciting here on the red line, but we have to do a background subtraction to see anything happen. And actually, the interesting changes are at the tens of nanovolt level. These oscillations come from taking, I think, a third-order polynomial from the background. And if we take a fast Fourier transform of this data, we see a bunch of distinct peaks here. So it can be difficult to make these different techniques work, but the payoff is that they can be really sensitive. Okay, a technique that some of you might have done already is just conventional transport. There's a lot of thinking that goes into doing this properly and to get nice data out of it. This cartoon just shows what we might have for a typical sample. Often they're plate-like, and plate-like samples can sometimes tell you about the electronic anisotropy of the sample. This might be a two-dimensional Fermi surface sample, and you can see I've set up the current to go vertically through the sample from top to bottom. For some samples, that's actually the path of highest resistance. And when we're measuring resistances, it's easier, life is easier when the resistance is higher. If you're trying to measure a micro-ohm, it's nearly impossible. But if you're trying to measure an ohm, it's not that difficult. When we're doing transport, we want to think about using clean single crystals with good triple Rs. The triple R is the residual resistivity ratio. It's kind of a way we screen samples from cooling them down from room temperature down to low temperatures. How much does the resistance change? How good of a metal is it? We need to set up 4 good contacts on the sample to avoid measuring the wire resistance of the probe. That's why we don't do 2 contact measurements. And we want to use reasonable currents for a good signal-to-noise ratio, but also to avoid self-heating. And I heard Tim and Eric both talk about this before. This means low resistance contacts. If you make a contact on your sample that's a kiloohm, and you're putting a huge amount of current into it, you're self-heating the sample at its surface. It's like you've attached a little heater to it. And from experience, it's easy to measure things, voltages that are at the millivolt level, or even microvolts aren't that difficult. The nanovolt level is nearly impossible. So we just keep these simple relationships in mind, Ohm's law and the power law. If you have a 1 microohm sample, even if you're putting a milliamp into it, that's a nanovolt. That's probably going to be impossible to measure. You're not going to be able to amplify it enough to get a good result. But if you dump a lot of current into it, it's possible that you'll heat up the sample and you won't get good results in that way either. So just rules of thumb to keep in mind as you're doing transport measurements. Yeah. This way? Yeah, so if you had something where the conducting planes are in the plane of this brick, if you put the current through the sample vertically, it's assumed that the current will spread uniformly. So this is what we would call an interplane measurement if this was a two-dimensional sample. Yeah. So in the assumption that this is a 2D sample, yeah, I would probably measure interplane like this. So, yes?
The other thing you can do if you have a low resistance sample is whack it down and thin it out, decrease its cross-section and increase its resistance. Or if you have access to a focused ion beam machine.
Okay, hold on. Spoiler alert. Oh, I was going to say, yeah, okay. Okay, you know, I was working on it. I'm getting there. I didn't do that. So. Okay.
You went straight to the good one.
Yeah, well,
Most expensive solution as always.
yeah, well, but I don't have access to one of these. But a guy who's worked pretty often with the MagLab, Philip Moll, has developed this technique where he uses a focused ion beam to basically obliterate most of the sample. So you can see the dimensional scale here is 50 microns. So he blows away most of the sample and he leaves these thin channels to actually measure. And you know from the cross-section of a wire, the thinner a sample, the higher the resistance, it makes it easier to measure. And you can also isolate these along crystallographic axes. So he might say, I want to know the resistance along specifically the B-axis of the sample in some specific orientation, and he can carve it out this way. This not only has the advantage of being higher resistance, but he can also take a crystal that might be disordered and isolate it down to a clean domain in the crystal because this whole spacing is less than 100 microns squared. And taking a sample like that, you can get pretty clean results, even in pulsed fields. I'm not on a hiring committee for any job to pursue somebody like this, but he's the name I see come up again and again for doing this technique. And I don't know of a second person that's become a guru of this technique as well. It's really expensive to use a fib to do this. So if any young scientists were to pursue this as a task that they could become good with, they could probably pretty easily search for a job. It costs about $150 an hour to use a fib. So when people use these, they want to use them efficiently and get good results. So again, I don't think I've heard of anybody else at the MagLab coming in with fibbed samples, but Philip Moll was in high demand and now I think has a permanent position in Dresden. Yeah.
I'm sorry.
Yeah.
So when you apply magnetic field, which direction is perpendicular to your sample line?
In this specific case, it would probably be up through this purple surface.
I'm sorry, the top.
This one?
Yeah.
Yeah. In my cartoon, that makes more sense in my head. These are the conducting planes, and the magnetic field would be up perpendicular through the sample for this interplane measurement, and that would give Fermi surface. You would be able to detect the Fermi surface. If the field was this way, sideways through the sample, we wouldn't be able to detect anything. But it depends on the actual Fermi surface in the sample. Yes? Yeah. I mean, if somebody brings a fibbed sample, that's a best case scenario for us, that they brought something with robust contacts that we can attach something on our probe to, as long as it fits within the sample space that we have for the magnet.
Can you go back to the slide right before this? So the 2D Fermi cylinder, where would you say that is?
Yeah, I shouldn't claim that you can't tell from the photo what the Fermi surface would look like, but
If you did have one that was this way, then, or whichever way, where would you orient the leads and the magnetic field?
well, Well, in this case, I'm claiming that if I had that black brick in the orientation of the other slide, this would be the Fermi surface of it, and you'd want the magnetic field perpendicular to it.
Okay.
And Lorentz forces force the trajectory of the electrons to go in a circle on the outside of the Fermi surface. Okay, so
This is why we mount many things on rotators.
yeah, and that's the purpose is when it's on a rotator, we kind of explore what we're going to see by tilting the sample around until we detect the Fermi surface. Okay, say you have difficulty putting contacts on your samples, or it's impossible in some cases. We also have contact-free ways of measuring quantum oscillations. In this case, we use a TDO circuit, TDO being tunnel diode oscillator. This is a photo of the end-on view of a coil of wire with a single crystal in the middle. And this coil of wire makes an inductor that's part of this resonant circuit. This dashed box shows the part of the circuit that's down at low temperatures, including the tunnel diode shown here. If you bias the tunnel diode into this negative conductance region here, it creates a resonant frequency in the circuit. If the sample changes resistance or magnetization, the resonant frequency for the circuit's going to change too. And we have some data to show that. Down at the bottom, we have a 50 megahertz resonant circuit frequency. And we've mixed that down to 2.5 megahertz. When we sweep the field up to 35 Tesla, the overall circuit frequency changes by about 2 megahertz. Okay, there's nothing interesting to see in this red trace, but if we take the derivative of this trace, we can see tiny changes you can't say here in this black trace. So there's actually lots of oscillations in this raw data. If we focus on just the low field end of the data and we subtract a background away, between 3 and 6 Tesla, we see oscillations this small. The amplitude of these oscillations is as small as 50 hertz for the frequency change. With our resonant frequency of the circuit being 50 megahertz, that gives us 1 part per million resolution using this measurement. So it's incredibly sensitive and a useful technique that you can use that's contact-free. You can basically just drop a sample into a coil and do the measurement. And this is also useful because you can put the coils inside pressure cells, and without adding contacts, check out the pressure dependence of the Fermi surface. Okay, if you've collected a lot of data and you need to figure out what is it actually telling you. Okay, so Lifshitz and Kosovich came up with this formalism to describe the oscillatory data that we get. This can be taken in magnetization data or normalized conductivity. Long formula, but we recognize some parts of it already. This oscillates as a function of inverse magnetic field. Okay, cosine term, inverse magnetic field. And we can learn information from these damping parameters, how the oscillation amplitude changes as a function of different things. For example, this temperature-dependent damping term is written out here. And if we look at some data, you can see that the lowest temperature data has the largest oscillations. And with larger temperatures, the oscillations go away. How quickly those oscillations go away can be mapped out and plotted. So you can either subtract the background and see how the amplitude of a peak changes, or take an FFT and check out the temperature dependence of your FFT. So this is the oscillation amplitude versus temperature, and if you fit it with this damping term, you can extract the effective mass. The effective mass of this material was 0.23 barrel electron masses. If the fitting parameter moves to, if this fitting goes to lower temperatures, then you might have something like a heavy fermion. You can have as much as hundreds of barrel electron masses. And if this moves out to higher temperatures, you can have a very low effective mass, a very small effective mass. So if from this temperature-dependent damping term you've already extracted the effective mass, you can go on to the next term, the Dingle term. And this talks about how the amplitude changes as a function of inverse magnetic field. Okay, so if you see the amplitude changing in a certain way, you can fit that. We already know the effective mass. Everything else is constants. And you can find the Dingle temperature of the material. That's usually a measurement of how clean the sample is, how easily the carriers are moving through the material. From that Dingle temperature, we can actually find the scattering rate and the mean free path through the material. Okay, so as we progress through, we know the effective mass. We know the Dingle temperature. The spin term takes into account that the up and down spin carriers have slightly different energies. So in this damping term, at some point this argument is going to be an odd integer, okay? Some constant, the g factor, the mass over the bare electron mass. When this equals 1, 3, 5, etc., we get cosine of pi over 2. And when that happens as you're rotating, you'll end up having the oscillation amplitude go away. We call these spin zero angles. Okay, if you do a very careful analysis of angle dependence, you can actually go backwards and find the spin factor for the material, which for electrons is usually close to 2. Okay, so this is the information we can extract once we've actually collected some quantum oscillation data. Okay, so what else can the Fermi surface tell us about actual physics going on in a material? So this example is cerium, rhodium, indium 5. Here's the temperature versus magnetic field. When you go to low temperatures and low fields, you're stuck in an antiferromagnetic state. So if you move out in magnetic field, you go to an antiferromagnetic state with just a different range of ordering. And if you go to really high fields beyond 50 Tesla, it goes into the paramagnetic state. The phase boundary was determined by heat capacity measurements and de Haas van Alphen measurements out in Los Alamos. We did some Hall effect measurements here in Tallahassee, and we didn't see any quantum oscillations with the transport data, but the Hall effect did show us some kinks in the Hall signal, which tells us that something's happening to the carriers and helped us to further define these phase boundaries. What's interesting about this study is the fast Fourier transform data, the stuff that tells us about the orbits. As you move up vertically in this plot, the amount of magnetic field we're looking at when we take the fast Fourier transform extends to higher fields. And the fast Fourier transform is evolving as you go to higher fields. What that means is that the Fermi surface isn't constant through the whole field sweep. There's a Fermi surface reconstruction as you get up to higher fields. What they found in this study is they compared the results here with a similar compound, lanthanum, rhodium, indium 5, and they don't see the same effect. So what they determined is that the 4f electrons of the cerium go from being localized at low temperatures and low fields to itinerant, so they can move around and contribute to the Fermi surface as you move out to higher fields. Okay, so a detailed Fermi surface study can tell us when electrons begin to contribute to the Fermi surface, especially when you know a comparison with a similar compound. Okay, we can change different parameters for our measurements, sweeping the magnetic field, cooling down the sample to lower temperatures. We can also continuously change the angle of a sample. Okay, especially with the rotator probes here in Tallahassee, we just hook up a motor and we can rotate more than 180 degrees for the sample. If we go back to our picture of our quasi two-dimensional Fermi surface from the strontium iron phosphide, this just kind of shows the shape. If we took a slice of this, this would be the cross-section of that quasi two-dimensional Fermi surface. What they call this, when it has the skinny parts and the fatter parts, is that it has necks and it has bellies. Okay? If the field goes vertically through the screen along this KZ axis, you'll get a different orbit frequency from the skinny part, the neck, and from the wider part, the belly. So that just gives you regular quantum oscillations that we've already been talking about. But if you rotate the magnetic field away from this axis, you'll have points where the cross-section across the Fermi surface will have points where it's equal between the Fermi surface all the way along. What that means is instead of skinny necks and wide bellies, it's a uniform Fermi surface orbit for certain orientations. What this means as far as looking at the data is shown here. We still see these fast oscillations. These are just the Shrubnikov-de Haas oscillations for measuring the sample, but these other oscillations here are what we call angle-dependent magneto resistance oscillations. Basically what you can get from this, and knowing the spacing of the Fermi surface, is the Fermi wave vector. Okay, if we take this and we slice it off and we're looking down from the top on it, we might want to know the shape of this. This is about a circle for this one, but if you do this kind of measurement, you can measure out from the origin and get the Fermi wave vector. And if you repeat this measurement by rotating the sample a little bit in phi and do it repeatedly, you can map out the entire outside shape of the Fermi surface. Okay, these are called, like I said, angle-dependent magneto-resistance oscillations, or sometimes they're called Yamaji oscillations after the guy that figured this out. Another person that used this kind of measurement was Suchitra. She came back with her coupe rates to Tallahassee in 45 Tesla. And they kind of had an idea of what the Fermi surface of this coupe rate looked like. There's a beta cylinder that's really hard to observe, that's faded here. But there's also an alpha orbit. And you can see the alpha cylinder doesn't have a lot of warping along the side. It's more 2D than being quasi 2D. And there's a gamma orbit as well, and this has a little bit more corrugation along the edge. So they know that there's three distinct frequencies from their fast Fourier transform, but they wanted to know more about the shape of the Fermi surface. So they took this sample and put it into one of these TDO kind of coils, and they continuously rotated the sample in 45 Tesla in the hybrid. So each of these different colored angle sweeps is at 45 Tesla, and when they went through an angle sweep, they adjusted the phi angle in spherical coordinates a little bit and continued and did another angle sweep again and again and got a complete set of this AMRO data. Because you can only learn about the Fermi wave vector from corrugated or warped two-dimensional Fermi surfaces, when they mapped out this Fermi wave vector, they knew it was from this gamma orbit. And they had an idea ahead of time of what the gamma plus the alpha orbit would look like. And basically, this black and this red trace is the actual data compared to a model they have of what the Fermi surface should look like. Okay, so this AMRO data is a powerful technique as long as you have a corrugated two-dimensional Fermi surface and not just a two-dimensional cylinder. Okay, so how might you actually physically do a measurement like this? Okay, we're talking about rotating something in theta and phi. Well, one way you might do this is with a two-axis rotator. What that means is we have a piezo rotator. This rotator moves around in a circle like this, like a CD player or a DVD player, when you send voltage pulses down to some little piezo elements in the base of it. Okay, if you take something like this and you put a sample platform on the top, there's all these little copper tabs that we have tiny samples attached to with little wires going to them, and those wires go through the center axis of the piezo rotator. Now you can fit something like this assembly, these piezo rotators, onto the probe in SCM2. Okay, so you already used this probe with Jihoon the other day when you were in the millikelvin facility. This dashed line is rotation around the rotation for theta rotation. So it goes around that dashed axis. And if you want to move phi, you send voltage pulses down the probe to the platform, and it'll move in the phi orientation. So that way you can basically cover all angles. You can get to any orientation with theta and phi rotation. So with the samples we put in place, we got a complete set of AMRO data. So again, angle sweeps, and when we complete an angle sweep in theta, we move the sample just a little bit in phi, 20 degrees. So it's 20 degrees different for rotating the sample in phi between all these sweeps. And analyzing all this data, once again, we find the Fermi wave vector of the sample. In this case, nature is kind of interesting. I don't know why this happens, but the actual morphology of the sample is that it grows in this hexagonal shape. And if you look at the Fermi wave vector around the Fermi surface, it's also kind of a hexagon. So that was predicted in band structure calculations, and that's actually what we found, that the Fermi surface grows, is observed in kind of a hexagonal shape. Okay, some other oscillatory phenomena you might see in a high field measurement. Strange things that we occasionally see here. These are quasi one-dimensional Fermi surface sheets. They're both on one side of the Brillouin zone. So when carriers move along these sheets, they both move in the same direction, shown by the red arrows. Because these sheets are warped, they have points like C and E where the sheets are closer together. When you get the magnetic field to a strong enough point, interference happens between the carriers at these close points. And even though this isn't a closed Fermi surface, an orbit can't go around it, because the carriers interfere, you'll see oscillations in the data from this green space shown here. And if you rotated the sample, you'd actually see the same kind of angle dependence you see in other samples as well. But this isn't a quantum oscillation. This is what we call quantum interference. The carriers interfere when the Fermi surface is closely spaced. If you have a one-dimensional Fermi surface, kind of like this guy shown from the top, and closed orbits in close proximity, you can also get magnetic breakdown. What that means is with a strong enough magnetic field, not only will the electrons go on this closed Fermi surface, but at some point they'll jump off this energy pathway and jump onto another part of the Fermi surface and complete an orbit like this. When you have magnetic breakdown, you can also have very strange effects. It doesn't have to go in this large circular orbit. It can also go in an orbit and skip to the inside of this pathway. So if you take a full set of data with the magnetic field for this sample, you'll actually get a fast Fourier transform spectrum that shows all the different strange shapes that this can take. The carriers can go along these closed orbits, the bigger orbits, and also any combination in between. So quantum interference and magnetic breakdown. Okay, a new way users have recently in the past 5 or 7 years started measuring things here at the MagLab is by devices. Okay, we have a thin sample here, graphene, black phosphorus, something like that. Yeah, Renee? This is my last slide. You're welcome. Okay, so this will be a thin material, maybe a few nanometers or maybe a monolayer of graphene. And they magically put small tabs for measuring transport on these devices. I don't know how they do it. They bring it to us, and then we don't make them here. But it's usually sitting on a substrate like boron nitride or something like that, and they'll have some backgate behind the sample. So graphene has this kind of linear dispersion relation. For what we're discussing, we'll just say that means it has a low effective mass. But what we can do with this gate behind the sample is apply an electric field across the sample, and that'll shift the Fermi level. Okay, so we can do conventional transport measurements like shown in this inset. We have a sweep up to 2-point-something Tesla, but we see quantum oscillations by measuring RXX. That's the resistance along the sample. But by measuring the Hall effect, we can also see the fractional quantum Hall effect at high fields, not by sweeping up the magnetic field, but by going up to 35 Tesla, sitting at a constant magnetic field and low temperature, but by sweeping the electric field across the sample, by sweeping the gate across the sample. Okay, this is a kind of a more modern approach that people are taking to exploring the materials in these devices. Okay, and I promised Renee I would finish, so I'm going to skip all the high pressure stuff. Okay. Just imagine how long you could have been here. So I'll skip over the summary as well because we already talked through all of it. But this is actually kind of the more important part is learning more. Okay, if you guys are going to do these kinds of measurements, there's one book that's a nice introduction, Band Theory and the Electronic Properties of Solids. If you want your copy signed, John Singleton's working in Cell 8 this week. So, this is kind of the Bible of quantum oscillation measurements by Schoenberg. It's everything start to finish you could want to know about quantum oscillations. So it's a difficult read, but it has all the details. And Ashcroft, Merman, and Cattell have some details about quantum oscillation measurements as well. And we already talked about Egan during the lab practical. So, all right. Any questions?